Okay, in this video we're going to be talking about Markov chains and stable state vectors. Now let me just go ahead and warn y'all before we get started. There's a lot of information in this video, so if there's ever a time where I'm going too fast, feel free to pause the video so you can catch up. So let's get started. What you're looking at right now is a probability tree where you have a choice of eating a hot dog or hamburger for the days of Monday and Tuesday. Now let's just make sure we can understand what's being displayed here. Um, all your choices for Monday are written right here. So these are all your Monday choices and these are all your Tuesday choices. Okay. Now making sure that you guys can read this, we're going to have a couple of simple little questions. All right. So if I was to say, what is the probability that you'll eat a hot dog on Monday? Well, if you're starting right here, what's the probability that you'll eat a hot dog on Monday? Well, that's going to be 60%. Okay, so this right here is 60%. Now, what is the probability that you'll eat a hot dog on both days? Well, going back up to our chart here, you are starting, now so we're dealing with multiple probabilities here. Okay, so I'm going to use purple. You're starting here. What is the probability that you'll eat a hot dog here? And that you'll also eat a hot dog right here. Okay, now notice it involves the 60 as well as the 25. Okay, so what we're going to do with those two probabilities is we're going to multiply them. So 60% times 25% will give you 15%. So there is a 15% chance that you would eat a hot dog on both days. Okay, now last example before we move on from this. What is the probability that you eat a hamburger on Monday and then a hot dog on Tuesday? Well, if you're sitting right here, I'm going to use this in yellow highlighter here, a hamburger on Monday and then a hot dog on Tuesday. Well, that deals with the 40% and 70%. So that is 40% times 70%, which I believe is 28%. So there's a 28% chance that you'll eat a hot dog on Monday and then a hot dog on Tuesday. Okay, hopefully you got that. So let me clear out the chart so we can start something new. Okay, let's go back to our chart here. And the question originally was, what is the probability for lunch for the next 2 days? Okay, and there's enough information that's gathered here. See, you only have Monday's information and then you only have Tuesday's information. And that's all you need. Okay, these problems are only going to give you the first 2 days. All right, but you're going to start running into questions of what are the probability that you'll eat a hot dog, or what is the probability that you eat a hamburger after, day 5. Okay, so since you already have 2 days distributed, if you were going to use this same procedure, meaning if you were going to branch out your tree to day 5, it's going to look like a pretty involved tree. Okay, and it's going to probably just be more work than it should be. And because of that, we are going to create a matrix. Okay, we're going to use matrix operations for this. Okay, now the first thing we got to do when we are building our matrices is we got to put things in matrices. Obviously, the first thing we're going to do is we're going to take this 40 and 60%, and we're going to put that into what is called an initial distribution. And you'll always pull these numbers from the first two. Okay, 60%, 40%. Now with the initial distribution, it will be a row matrix. Okay, so this will be a row matrix. So when I'm building it, I'm just going to build it right here in red. I'm going to put 60% first, and then I'm going to put 40% after that. There's my row matrix. Now you got to label this. 60% that I'll eat a hot dog, which I'll use as H, and 40% that I would do a hamburger, and I'll just do HA for hamburger. Okay, so pretty simple. Now the next thing you need to do is you need to put this information into a matrix as well. Okay, and what this information is going to be put in is what is called a transition matrix. A transition matrix. Now, things about a transition matrix is that it is a square matrix. All right, so it's a square matrix. And also, another thing to note is that each row adds up to 100%. And I'll explain that in 1 second. So we're dealing with four numbers and it has to be a square matrix. So that means we are going to be dealing with a 2 by 2 matrix. So I'm going to build it right here because I'm kind of running out of room here. Now remember, you need labels. That's going to be one there, there, there. Now notice how going back to our initial matrix, or the initial distribution matrix, how hamburger is wrote first, is written first, and then hot dog is written first and hamburger. I get it right. We have to do the same thing for our transition matrix. So our hamburger is written first. I'm sorry, that's hot dog. I get it right. And this is our hamburger, and it's got to be hot dog and hamburger down the column there. Okay. Now, the way that you figure, the easiest way to figure out is figure out this first and then figure out this first, and everything else is pretty easy. So what is the hot dog to hot dog situation? Well, um, going back to my tree here, the hot dog to hot dog situation, that's 0.25 or 25%. Okay. Now, each row has to add up to 100%. So if that's 25%, that's got to be 75%. Okay. Now, hamburger to hamburger, that's 30%, which means this right here is 70%. So at this point in time, the hardest part is done, being able to create your matrices. Okay. So I'm going to pause the video. You copy down these two matrices, and then we're going to do some matrix operations. Okay. Hopefully you already have all this copied down. So let's go into why we're doing this. Okay. The reason we're doing this is because of the fact that we're trying to find the Markov chain, meaning basically finding a trend in the numbers. Now you might want to pause the video because I'm about to go back. All right. So we have a hot dog, hamburger, and so we're trying to find what is the likelihood that I'm going to get a hot dog and hamburger on like day 5 or 6. So let me write down my all my matrices right here. Okay, there's my matrices. Now, you remember when we first started this video, we were answering questions like, what is the probability that you'll be eating hot dog on both days? And then you have to go into the matrix, or go into this problem, and then go hot dog, hot dog. You have to go through the entire graph. Well, using your matrices, it helps you go ahead and get your answer without having to go through the chart. So if I was to ask you, what is going to be the probability, so what's going to be the probability, and I misspelled that, the probability of day 5. Okay. Now what I'm going to do is I'm going to take my two matrices. I'm going to multiply my initial distribution matrix times my transition matrix and raise it to the 5th power, which means to the 5th power, meaning it's on day 5. All right. And let's see what we have. Okay. Now one thing, when I was typing in my calculator, to leave these as percentages, I'm going to get very large numbers. So what I'm going to do is I'm going to convert all of these to points, because I'm just converting everything to a decimal, because remember how percents and decimals can get converted. So when I multiply all this out, my answer was 0.48 and then 0.52. Now remember, everything, this is hot dog and this is a hamburger. Now the question is, okay, what do these numbers mean? That means on day 5, I have a 48% chance of purchasing a hot dog on day, and which means I also have a 52% chance eating a hamburger. Okay, well, let's figure out day 10. Okay, which is pretty simple. Day 10, that will be d times t to the 10th power. And on day 10, once again, it's the same thing. It's the same thing. Now, if I was to do day 20, once again, I'm still going to get the same answer. Okay. Now, what happens is that your numbers eventually start stabilizing. Okay. And when they start stabilizing, it is called the stable state vector. Because what's happening is a stable state vector, and basically what's happening is that we have gotten to a point where our numbers never change. So you would say, or if the question was what was the stable state vector of this problem, you would say it was 0.48 and then 0.52, because these numbers never change. So that's how you figure it out. Let me know if you have any questions. Thank you.